Oh. Aha.
I wouldn't do that if I were you.
Why? Because it'll make a big mess?
No, it's the only one we have.
All right. But, hey, wait a second. Would you get out of here? I'm busy. Hope that was worth it. Hey, everybody. Welcome to this week's walkthrough video. In this week's laboratory, you're going to be verifying the acceleration due to gravity, 9.8 meters per second squared. You'll be doing this by dropping an object through a photo gate and collecting the data, analyzing the data, and using something called statistical analysis to help justify your results. But before we get into the details on that, let's talk about this week's pre-lab activity. For the pre-lab activity, you'll be using an app that you can download called Firefox. When you tap on Firefox, it opens up a whole series of experiments. Many of these experiments are sorted based off of the type of experiment that they categorize with, and in our interest we want to look at the acceleration without g. So we're going to tap on this one. As you can see, when you open up this app, you see that there's 3 blocks that are available to you. So I'm going to slide this to the side so you can see, but there is 3 axes that this phone is operating on. You can see, according to this image right here, that there is the x-axis goes this direction, y-axis goes to the top of the phone, and the z-axis comes out of the phone towards you. So what you'll do is now drop this in a very safe way onto a nice soft surface and try and capture the acceleration due to gravity. So now let's take a quick look at analyzing this data that you just took. You have your 3 axes, X, Y, and Z, and the way that you saw me drop it was down along the Z-axis, and I gave it a spin so that it would give hopefully a nice stable bed of measurements along the other 2 axes, X and Y. So let's zoom into each of those and take a look. So if we look at the X-axis, you just tap on that, you just zoom in, you see these 2 spikes here. And it turns out the 2 spikes are actually from it landing on the surface and having a sudden major acceleration. So those are basically useless information except for the fact that they show us that it was started or stopping motion. We can tap anywhere on here when we click on pick a data point. You tap on that point and it can show you what that value is. You click on pan and zoom, and even by zooming in further you can affect the information that's on your vertical axis. So let's kind of keep this between about 2 seconds and 2.6 seconds for my drop. Whatever works for your drop is something you want to best fit your space, but you want to make sure that you can see this pretty well. And we'll hit this button here, the 2 arrows, to go back out. We want to keep as selected. We want to keep this scale when we go out of this zoomed in space. You click OK, and you see that it's now zoomed in for that axis. So 2.6. So let's go into the Y data. We'll zoom in just like we did a moment ago. Let's see if we can move it into, okay, so there we go, 2 and 2.6, and let's just kind of zoom in vertically, and we can see again that there's a spike that demonstrates that this stopped. We can click on pick a data point, maybe set it right here, go back in there, and really take a look at how much space. So we're going minus 20 acceleration. We hit linear acceleration to go out, keep as selected again, click OK. And you see that these 2 scales are pretty comparable. So let's take a look at the Z-axis. Zoom in. And zoom in this way to really get ourselves a nice axis that can tell us. And you notice that one of the values that shows up is minus 10 meters per second squared. That sounds very close to negative 9.8 meters per second squared. And you notice because I gave it a spin, it seemed to stabilize so that the Z-axis continued to fall straight downward. And if we pick a data point, you see that you're about 9.08 meters per second squared. You know, tap on different points. If you try and drag it, it'll actually set up a slope, and you don't really need that. But here at the highest point, negative 9.67. So in your pre-lab, you were able to demonstrate with your phone that your acceleration is negative 9.8. We're going to click on this again and then zoom out, keep as selected, click OK. This is the graph that you're going to print, and you will highlight that this is the region where the fall was taking place, and if there's any information in this region during that fall for your X and Y axis that you want to draw attention to, go ahead and do that. And make sure that you write on your page what your acceleration due to gravity is according to your data. And that's it. So let's talk a little bit about data analysis. Last week, you worked on data and you got a little familiarity with correlations between position, velocity, and acceleration. You got familiar with how to work with Excel or other spreadsheet program and being able to apply trend lines that fit the data to some reasonable amount. But at the end of the day, we did not make analysis that was scientifically valid. All we did was we looked at some values and said they kind of agree. In this lab, you're going to learn more about what makes a viable scientific valid argument about whether or not two pieces of data are in agreement with each other. But before we get into that a little bit, let's take a quick look at what possibly you could do with the data. Now in lecture, you'll have by now, I think, covered all these kinematic equations. And if you notice, all three are under constant acceleration. And you can replace acceleration with the value of g in each of these. And depending on what kind of data you've collected, you can plot this information pretty handily at this point. So let's take the system that maybe makes most sense, just like you did in the previous lab exercise. And it seems like it makes sense, right? Because this could be nice, smooth fit to the data, and if it's accelerating from velocity equals 0, then your fit equation should be pretty nice and really get you 9.8 meters per second squared, which is fine except for this factor. When Excel or any other spreadsheet program makes a fit trend line, it adjusts them until they fit within some margin of setting that's within the system. But here's the catch. In this lab, you're only going to get 6 data points per drop. 1, 2, 3, 4, 5, 6. And you're trying to fit 3 coefficients to make that work. That gets sketchy. We know that we can make a line with just 2 points, but if you're not able to say for certain that the data is supposed to be linear, then a line may work mathematically but not be valid physically. So we have to be mindful of how we're doing our analysis. If instead of using position versus time data with 6 data points trying to fit 3 values, we use those same 6 data points for a linear fit of velocity versus time. Now we're doing 2 data points. We're trying to find 2 values out of 6 data points. We've basically made our argument that this fit goes with this based off of not just mathematical means, but also because of physically reliable means. This is based off of physical motion, and you have 6 data points that appear to be going in a straight line, and you can confirm that with your y equals mx plus b linear fit. Now, of course, it's always easy to cheat. We could just put all the acceleration versus time that's derived from this. You'll have a very truncated set, and it's a little too easy. Also, based off of the statistical analysis that you'll be doing, which we'll be talking about in just a moment, this is actually going to be stuff that you're doing in the course of it anyway, so this is a redundant exercise. So you'll be graphing your velocity versus time of the drops and extracting a linear fit from each of those data sets. Now let's talk about the statistics. So there are a number of ways to do statistical analysis of data, quite a lot, and that's why statistics is a very large field. But we don't need to get into that in order to make viable scientific analysis of our data. We can actually live quite comfortably just by establishing a couple of statistical standards that we'll use pretty much for the rest of the year. And these standards are percent error and percent difference. The difference between these two is percent error is when you're comparing against a known quantity, something that is for certain. Everybody agrees that this value is the correct value. Most often it's been tested multiple times and again. So we use percent error whenever we're comparing some experimental value against some known value. In this case, the known value is acceleration due to gravity, 9.8 meters per second squared. And then the other time is when we aren't sure for some reason or another that the value we're comparing against has some scientific benchmark value. So we use percent difference in this case where we compare either 2 experimental values to each other or some reference value that we think is pretty good, but maybe for some reason, like I said, doesn't have a benchmark characteristic to it. And so it's a minor variation of what we see here for the percent error. So for percent error, it is experimental minus the accepted value, so whatever you get in lab, minus 9.80665, make sure you get all those decimal places in there, divided by 9.80665, times 100 will give you your percent error. By comparison, if you're comparing measured values to each other, you put one minus the other and then divide it by the average of those two values. Doesn't matter which one it goes first. I'm not going to answer that question for you. I invite you to think about what this particular percent difference means. Consider that we have an object that has a true actual value, whatever that value is. And let's pretend that you're doing an experiment and it's the white chalk experiment. You are measuring compared to the value that you expect it to be the actual value. You make measurements, boom, 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 boom. 5 measurements land on one side of this as being a little bit shorter than the value, and one of them lands on the other side. When you perform your measurement, you are performing percent error because it's a known value, and it gives you an assessment of your data compared to this known quantity. By contrast, if we don't have a known value, so now we're doing the pink chalk experiment, you have one value over here and these 5 values over here. When you perform percent difference, you're measuring them compared to each other. So one is the measurement of the viability of your ability to measure the true value, and the other is more or less how well your own experiment is able to agree with itself as you perform an experiment. There's a few different ways to look at this interpretation, but this is one way to think about percent error versus percent difference. It is considered a standard in most scientific circles that 5% is a threshold of importance. In other words, if you make measurements that are far less than 5%, there are factors that influence your data that you want to still think about when you're talking about your analysis, but those factors were not significant enough to affect your overall ability to measure accurately 9.8 meters per second squared and compare it to the true value. When you exceed 5%, usually that means that there were errors, and some of those errors were significant enough to influence your data. So you want to start thinking about what percentage error, when you're making your measurements and doing this lab, what values are you measuring percentage error, which ones are you measuring percent difference, and start thinking about how you're going to comment about how these impact one another. Photogate is a simple sensor which beam of light travels from one side to the other along a straight path, and anytime you block that, you find that the red light flashes on, indicating that it has triggered a stop, or at least that it's blocked. For example, what you will drop are these picket fences. These picket fences consist of dark bands with open space where light can pass through. These trigger the start and stop of the timer for the data collection that we've set up in the Capstone software. You'll notice that even though they are different weights, this is heavier than this one, that they have the same spacing, so they'll do the same triggering of the system with the Photogate. You'll notice that the heavier one does have an extra one, so you will have an extra data point for that set of data to evaluate. To start out, you connect your Photogate, unfurl it. We're going to connect it to the 850 sensor as we did with the previous one, only in a different location. This is a stereo cord pickup. And you're going to want to situate it, make sure that the cord is probably safely wrapped around one time and then fed away from it so that it's going in the opposite direction that you're going to have your Photogate. And you want to situate your Photogate over in such a way that something can fall in between it and land down below. You situate it over top so that it doesn't touch the sides or collide in any way. You want to drop it straight down, and this can begin triggering the Photogate every time a dark band passes through. Hold it vertically, and you allow it to fall straight into the box. Make sure that you hold it so that it begins falling before it enters the Photogate, and then you release. 3, 2, 1. And so long as you set your box down below to catch these, they should not come out damaged, and you can repeat the test over and over again. Once you're ready to collect data, you simply click the record button down here. And what differs between this experiment and the last one constantly took live data. This one is waiting for triggering from the Photogate, so you can go at any point, and it's only going to give you time. It will calibrate the time according to where it is that you actually start the clock, and you click start when you're ready to go. That way your scale goes nicely. But watch what happens. We're dropping the heavy one first. 3, 2, 1. I think you can hear from that experiment did not go well. So we'll try again. It's still collecting data, so I can drop again. We don't have to stop the run. That time it went through more effectively. I'll go ahead and do a third one just to be sure. 3, 2, 1. So now we'll stop this. And let's zoom in on each set of data and see what we got. You can grab it and shift it, grab this arrow down here, just explore, ask questions of me or the TA, your TA or your LA in class. They'll also be experts at this. So you can see this data is just not really good. You see wobbles that are uneven and then a sudden sharp jump because as it fell, it bumped into the photo gate. So this piece of data is no good. So we scooch further along, see what came next. So here we are. Zooming in, that seems like a pretty nice piece of data. Look how you're scrunched up though. You may have seen it's better to present your data over a larger area because you want to fill up the space and look for any interesting changes to the data. So smushing it down, that's not good. So zoom this down. Let's go and fill up the page with this. There we go. Now it's in the middle of the page. Come up here to the 3 blue dots with the yellow highlighter. That's your highlight range dot. That's your active data square. And you just make sure that you adjust your screen so that your active data is good. Remember, you export this data. Once you change the data to decimal places, export this data to Excel, and you can manipulate this in there and get that practice as well. Got this active data here. We're going to come over to the function line, this line right here, which is bunch of blue dots with a red line through them. Again, we're going to choose linear because this is a speed versus time, the slope of which should by now be recognizable as acceleration. And take a look, our acceleration for this one, 9.72. That's pretty good for some data analysis. You will notice that you also have a plus or minus value. This is the error of the fit of this data. This is an internal calculation for how good this data is fit by this line, which is not quite the same as the error analysis that you'll be doing. But it's important to know that there is a difference between them and what they might mean. Now, well, that does it for this week's walkthrough. If you have any questions, as always, talk to your TA, talk to your LA, talk to me, talk to your classmates. Don't forget that we have the Physics Help Center. And don't forget that you can always contact your TA and send in a rough draft of your lab right before you submit it so that we can give you some feedback and help you continue to polish your work. I'd like to thank Future Me for coming in and helping out with a little bit of this entertainment. Future Me, come on in. And a little bit of performance for everybody. Time travel's cool. Back to the future with you. Until next time, we'll see you in the lab. Thanks, guys. I'm just trying to work, and they keep calling. That seems reasonable. All right. Oh, wait. You get out of here. Okay, that was just some terrible acting. We'll try that again. Okay. Go blah, 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 blah.
Ready?
Yep. 3, 2, 1.
Oh, that didn't work out.
That's okay. That's why we have takes. And go. Hopefully you've enjoyed this video. That's just a terrible amateur thing to say, isn't it? Thanks, James. All right. Well, so one more try. Keep looking at the camera. I will look at like I'm making eye contact with myself. I don't know what to say. And these are the outtakes.